who will be telling us something about stochastic matchings.
Thank you for the introduction. Hello everyone, my name is Amir. I'll be talking about our paper with Sohail and Alma at Northeastern and Ronit at MIT. It's about in and out LCAs, local computation algorithms, and its applications to stochastic matching. Okay, so let's define LCAs. First, consider a setting where both the input and the output are very large, and so you want to access or compute only a part of the output without reading the whole input or without computing the whole output. For example, in the context of graph problems, the input would be a graph, and you would have this globally defined output like a maximum matching or vertex coloring, and you would ask the algorithm these local questions about it, whether an edge appears in the maximum matching or what is the color of this vertex in the vertex coloring. And essentially what you want from the algorithm is that once its randomness is drawn, you want it to implicitly fix a global output. And what you want from the algorithm is to grant you query access to that output. So let's take a closer look at this. The algorithm is given a graph G and the prompt U which is a vertex, and it wants to compute the output on. Then what it can do is read parts of the input. How can it do that? It scans the adjacency lists. For example, it would start with the prompt U, scan some of its neighbors, and then scan some of their neighbors, and eventually explore this small local subgraph around this vertex U and use the randomness it has and this subgraph it has explored to compute the output on U. And for the purposes of this result, we have assumed this model of randomness where each vertex has its own local random tape that the algorithm gains access to while at the moment it has explored that vertex. So let's now talk about in and out LCAs. The ultimate goal with these LCAs is to bound the amount of dependence between the different parts of the output. So you want the output on the different vertices, for example, to be as independent as you can get them. And the way we achieve this is by bounding the number of inquiries and outqueries for every vertex. So what does that mean? Let's start with outqueries. Let's say the algorithm is given this vertex U and it explores some subgraph around it. The set of explored vertices is the set of outqueries. And this number of outqueries often plays a key role in the analysis because it serves as a proxy to analyze the runtime of your LCA. So with that definition, let's look at a lemma about independence. Let's say we have an LCA A and two vertices U and V. We define this collision probability delta UV, which is the probability that when the algorithm is run on U and when the algorithm is run on V, the outqueries intersect. So they queries some shared vertices. The claim is that if this collision probability is small, then the output on these two vertices is going to be close to independent. A simple case of this claim would be when the collision probability is 0, so the outqueries are always disjoint. In that case, the outputs are exactly independent because the randomness they're using is completely disjoint. So now that we have this lemma, the question is, how do we bound the collision probabilities? And the thing to notice is that simply bounding the number of outqueries is not going to be enough. So if you consider this example, you've got U1 through UN. They all have a very small number of outqueries. It's 1. But as it happens, that one outquery is the same for every one of them. And that can make the collision probabilities very high. And if you look at it now, the output of U1 through UN could be determined by the local random tape at V, making the outputs on them very dependent on each other. So if you want an algorithm to have independent parts of the output, you want to avoid this case. Such a V should not exist. So then the inquiries come in. The inquiries is the simply the inverse of outqueries. So if V is in the outqueries of U1 through UN, U1 through UN form the inquiries of V. And to rule out that case, we need to bound the number of inquiries. And now I can state our main result about in and out LCAs. Let's say you have an LCA such that for each vertex, the number of inquiries and outqueries is bounded in expectation by some values Q plus and Q minus. We call these LCAs in and out LCAs. And the claim is that if you take any vertex U, the sum of the collision probabilities with this vertex U is bounded by Q minus times Q plus. And that sum intuitively tells you about the total amount of dependence that's going on between the output on U and the other parts of the output. That's it about in and out LCAs. I'll now move on to a stochastic matching. I'll just state the problem and our results. So we're given a graph G and a realization probability P. What's going to happen is a realized subgraph is going to be formed by including each edge of G with probability P independently. And the algorithm doesn't know what this realized subgraph is. So what does it do? It's going to query a subgraph Q and learn what subgraph of these queries has been realized. The goal is for the algorithm. So let's call the realized subgraph GP, and let's call the parts we have found out about QP, the ones that were queried and realized. The goal is for the maximum matching in QP to approximate the maximum matching in GP. So in expectation, it should be at least alpha times as large, where alpha is the approximation ratio. And the idea is that these queries are logistically difficult to make, so you don't want to make many of them. The queried subgraph should be sparse. And you want to make them ideally non-adaptively, so the queries should be fixed up front. Let's look at some trivial examples. One thing that the algorithm can do is querying all the graph, Q equals G. In that case, the approximation ratio is going to be perfect. It's going to be 1 because it knows all the realized edges. But it can be very dense. The queried subgraph is as dense as G itself. Another example would be querying a maximum matching in G. Then the queried subgraph is pretty sparse, but the approximation ratio can be bad. For example, if the graph is a complete graph and P is constant or even log n over n, then with high probability, this realized subgraph GP is going to have a perfect matching. On the other hand, the specific edges that the algorithm has queried are going to be realized with only a probability P, which means the approximation ratio is going to be P, which is not desired. Okay, so here's a summary of previous results and our result at the bottom. You can see there is this trade-off between the approximation ratio that you can get and the sparsity of the queried subgraph, here measured in the average degree of the queried subgraph. And there has been a long line of work getting better and better constant approximations using degree that is polynomial in 1 over P. And there has been this other paper that gets 1 minus epsilon approximation, but it uses degree that is quasi-polynomial in 1 over P. In our result, we get best of both worlds. We get 1 minus epsilon approximation using only poly 1 over P degree. And there is a simple lower bound that shows you need at least 1 over P degree. Okay, so I won't talk about the algorithm. I will just say that the algorithm is very simple. Our main technical contribution is the analysis of the algorithm, and that's where these in and out LCAs come in. The way the analysis goes and is that we want to show that QP has a large matching, and the way we prove it is we construct a large fractional matching on it. The way this fractional matching is constructed is by combining 2 different fractional matchings. And on a very high level, for them to combine well, you need the fractional matchings to have independent parts. So you don't want if you know an edge is appearing in a matching, you don't want that to reveal too much information about the rest of the matching. And yeah, that's it. Thank you.
Any questions?
I have a question about the stochastic matching problem. So you could also imagine that I could query some part of the graph and then produce some estimate for the maximum matching size rather than just looking at the maximum matching size on that subgraph.
Right.
Like, is there any more power? Like, could you give an estimate which is not just like the maximum matching on this subgraph?
Yeah, I'm not aware of any results like that. These results usually also compute the edge set. So it makes sense to only look at the realized subgraph of what you have queried. Yeah, I don't know. I haven't thought about any, just approximating the size based on what you have seen.
Any more questions? Yes.
If we want to get something query complexity close to 1 over p, I mean, what's the best? Do we know what's the best approximation we can get? Is there any results on that?
Yeah, that's the last one in the table. It's 0.68.
It's 1 over p. It's exactly the.
It's.
Okay.
I think the power of
P.
there might be a log 1 over p somewhere, but the power of p, I think it's 1 there.
Okay, any final question?